Now that we've set up the density matrix, and in particular have added in these ideas of population and dephasing relaxation times, we can use these to solve a problem. The one we'll look at here is the interaction of a two-level system with an oscillating electric field. This is actually quite a good model for the interaction of light with atoms, and it solves an important problem that has been with us since our first attempts to use time-dependent perturbation theory to look at optical absorption. Specifically now, we'll be able to get rid of the infinitely sharp absorption lines of our earlier models. This will give us a much more realistic model for optical absorption.
Now we want to see what happens when we apply an oscillating electric field, so that could be of this form here, that is E0 some amplitude times cos omega t, for example, although we often prefer to write these out using complex exponentials here. And we are applying then that oscillating field to our two-level system. We can simplify our algebra and the results somewhat if we define new what we can call slowly varying quantities. This beta 21 of t is rho 21 of t times e to the plus I omega t, and beta 12 of t is rho 12 of t times the exponential of minus I omega t. Using these takes out the underlying oscillation at frequency omega from our algebra. So there's a frequency omega oscillation that is buried in here that we're taking out in also this term as well. And these terms here are then slowly varying in that that oscillation has been taken out of those algebraically. We can then rewrite this equation we had for the off-diagonal terms in the density matrix, and also the equation for the diagonal elements, the population difference, using these elements and dropping any terms that come out to be proportional either e to the plus 2I omega t or e to the minus 2I omega t, on the presumption that terms like that will average out to 0 over timescales of cycles, and hence they will make relatively little contribution to the resulting values of these quantities. Hence we obtain approximately these two equations. This one for the population difference, and this one for the off-diagonal terms, where we've taken out the underlying omega oscillation from them. These equations are often known as the Bloch equations, and they were first derived in the field of magnetic resonance. Now, we defined beta 21 to be this and beta 12 to be this. We know the density matrix is Hermitian, so rho 12 is equal to rho 21 star, and so beta 12, which is this, is equal to beta 21 star, which is this. Now we can evaluate the ensemble average of the dipole moment of the system. We previously deduced that this would be the dipole element here times rho 12 plus rho 21. And here we have, substituting using these expressions here, that means that the dipole moment ensemble average is this number times these two terms, just substituting for the off-diagonal density matrix elements. And equivalently, because of this relation here, we can rewrite that in the following form with just a little algebra between these two lines, where this is the real part of beta 21 and this is the imaginary part of beta 21. Now let's solve in what we call the steady state. That is, we imagine we've got a steady monochromatic light field shining on this, and it's been there for a long time, and so the system has settled down into what we'll call its steady state behavior. And in steady state, rho 11 minus rho 22, the population difference between the states, will have settled down to some value. So once we've had the field on for a long time, the population difference will have settled down to some new value, and hence the time rate of change of it will be 0. Similarly, any coherent responses will have settled down to follow the appropriate driving field terms. So we expect d beta 21 by dt also to be 0. There will still be oscillation in the off-diagonal terms of the density matrix, but this slowly varying part will have settled down and it won't be changing in time anymore. Remember, the applied field was at frequency omega, and this term has that oscillation taken out of it. So, setting the left-hand sides of both this equation and the second equation here to 0, we can solve the resulting simultaneous linear equations in the two variables beta 21 and rho 11 minus rho 22. So we're going to set this to 0, we're going to set this to 0, and then we have two simultaneous linear equations involving only these two quantities. So we can solve those. And we're going to leave the details of this as an exercise. Now, we typically like to use this capital omega as a variable. It's a essentially almost dimensionless version of the product of the magnitude of the electric field and the electric dipole moment. It's technically got dimensions of angular frequency. And then with that simplification, we can write down this resulting solution then. This is our steady state solution, that rho 11 minus rho 22 is this equilibrium value of that same quantity times everything that we see here. That's the result of the solution of those two simultaneous linear equations with this minor change of notation. And similarly, we can solve for the imaginary part of beta 21 and the real part of beta 21. So these are the results of solving those two linear simultaneous equations with complex values in at least parts of them. So let's look at the actual behavior then that we get with an oscillating field driving the system. We presume that we have some large number, this capital N here, of such systems, if you like, atoms per unit volume. The population difference per unit volume between the number in the lower state and the number in the higher state is therefore just delta n, as we can call it, which is the total number of the systems times this fractional difference between the lower state population and the upper state population. And in the absence of the optical field, the population difference is just this one. This would be the equilibrium value. This might be a steady state value, but this would be what we'd call the equilibrium value once we turned off the driving field and left the system for a long time. Well, using this expression here and this expression, we can rewrite this equation in the following form. And this is telling us what the population difference is in the steady state if we're driving this system with an intensity, that's what this really is here, an optical intensity, at some frequency omega, when the separation energy between the two states is h bar omega 21. This result then tells us how the population difference varies as a function of the optical intensity at frequency omega. In general, in electromagnetism, we can define the static polarization of a material as being essentially what we call a susceptibility times the electric field. For historical reasons, there's also a constant in here, which is known as the electric constant, but it's got no modern physical significance. So basically, the polarization is the susceptibility times the electric field, with some dimensional corrections for historical reasons. When we have an oscillating field, the response of the medium, and hence the polarization, can be out of phase with the electric field that's driving it. And then it's convenient to generalize this idea of susceptibility a bit. We can formally think of the susceptibility as a complex quantity with real and imaginary parts, and we can call those chi prime and chi double prime, respectively. Or equivalently, we can explicitly write the response to a real field, E0 cos omega t, as this form here, that the polarization would be the driving amplitude, with our dimensioning constant in here, times some part that's in phase with the driving field at cos omega t, and some part that's 90 degrees out of phase with it. And just how much of each there is determined by these two numbers, which we can think of as the real and imaginary parts of the susceptibility. It is also generally true in electromagnetism that the polarization is the dipole moment per unit volume. And hence we can also write that the polarization here is n times the ensemble average of the dipole moment of a typical system, a typical atom if you like. So we've got n atoms per unit volume, so we have to multiply that up to get the total polarization, which is equivalently the dipole moment per unit volume, the total dipole moment per unit volume. Hence, using this expression that we figured out before, we can write it down in this form as we deduced. Then, with this definition here, and with this choice also here, we can explicitly write formulas for chi prime, the real part, and chi double prime, the imaginary part of the susceptibility. If we do that, we obtain these expressions. In electromagnetism, the real part of the susceptibility, the in-phase response, is what's responsible for refractive index. That is, if we put in this polarization in its relation to the electric field into Maxwell's equations and work through that, we would find that this real part is what's responsible for refractive index. That's the factor by which the speed of light is slowed down inside a medium. And the quadrature response, as we might call it, the 90-degree phase-shifted response, or the imaginary part of chi, or this chi double prime here, is what's responsible for absorption of energy, or optical absorption by the medium or the material. Well, at small fields, for a two-level system then, which we've been examining, this omega is a very small number. We're presuming we're going to say that E0 is not 0, but it's very small here. So then that term with omega in it essentially drops out of this formula here, and we're left with this expression for what the real part of the susceptibility, that's the refractive index part, will correspond to for our two-level system. So that's a function that looks like this. So this is for omega below the center frequency corresponding to this transition, and this is for omega above it. And this susceptibility here makes a positive contribution to the refractive index when we're below the transition frequency, and a negative contribution when we're above it. And similarly, we can plot out the imaginary part of the susceptibility, or the chi double prime, which has a formula like this. And that corresponds to this kind of shape. This is known as a Lorentzian absorption line.
Note that, finally, we've eliminated the delta function behavior of absorbing transitions that we got from simple time-dependent perturbation theory, for example. Now we have an absorbing line with a much more reasonable shape, with a width in frequency of the order of 1 over T2. So the more dephasing collisions there are with the atom, the wider the absorption line. Incidentally, any process that leads to the recovery of the atom from its excited state back to its lower state will also cause a decay of the off-diagonal elements. So even if there are no additional dephasing processes, the absorbing line will still have a width. When the only recovery or dephasing process is spontaneous emission, the resulting line width is called the natural line width. We can view the line width of the absorbing transition as being consistent with the energy-time uncertainty principle. If the state, or the coherence of the state, only persists for a finite time, then the state cannot have a well-defined energy, hence the line width.